Hi, this is Professor Fernandez, and this is video 1 in lesson 9. The topic here is differentiability, and we'll talk about differentiability in the context of this example from Calculus Simplified. So let's take a look at what the example says. We have here consider the function graphed in figure 3.7. There it is. And at what points in the interval between 2 and 4, not including 2 and 4, open parentheses, is f not differentiable? Also for part B, at what points in the same interval is it discontinuous? So you can see the intent of this example. We want to compare differentiability and continuity. And at the end of the video, I'll tell you exactly how those two relate to each other in terms of a theorem. But for now, we just want to run through this example. Okay, so let me remind you what being differentiable means. First of all, I might want to point you to video 8.2 in this series for a review of the limit definition of the derivative. So I've also put it down here, and I'll talk about it in a minute. But why do I point this out? Well, differentiable is, in its simplest form, about the derivative exists. So f prime of a exists. And we have a definition for f prime of a. I'll zoom in here. This is the limit definition. So recall that if f is a function, the derivative f prime of a at x equals a is defined by this. And what does this say? Remember, we talked about this in that video 8.2. This numerator is the change in y values between x equals a and x equals a plus a little bit of a change in x. And the denominator is delta x. So this numerator is fundamentally a slope, right? It's the slope of the secant line. Remember that geometry. And then we take the limit as delta x goes to 0, and that's how we get the slope of the tangent line, provided the limit exists, right? So this is where we're talking about, is the function differentiable at a, or is it not differentiable? That depends on whether this limit exists. And because we're talking about limits, and we've talked about lots of limits in this video series and the course, we know all about when limits exist and when they don't exist. Okay, so that's sort of the review. So I'm going to go back here, start applying some of that in this example. Okay, so what I'm doing is I am scanning the function here. I'm looking for points in this interval at which the slope of the tangent line does not exist. So let's just think about that here. So I'm going to draw a graph. Here we go. There's the graph, and I've drawn the tangent line at this point x equals a. The slope of that tangent line exists. Great. It looks like it would be 1 or 2 or 3 or something. What are some ways in which the slope of the tangent line may not exist? So I talk about this in section 3.4 in the book. So here's a different graph. Here's a graph that goes like this. At this point, the tangent line doesn't even exist, much less its slope. Why do I say that? Well, you know, if we were thinking of this point and comparing, taking another point here and drawing the secant line, there we go, right? And as this point gets closer, this green point gets closer, maybe go over here, draw the same secant line, over here, draw the same secant line. You can see that as I approach, in other words, this is my a plus delta x, right? Delta x in this case is negative because this point is to the left of a. In other words, as delta x goes to 0, the secant line that I get, if I declutter here, is the line that respects this kink from the left-hand side. That's the secant line I would get. However, if I start, pick a point on the right-hand side, and now this is my new a plus delta x. So in this case, delta x is positive because this point is to the right of a. So if I pick that point up there, the green point, and I try to draw the secant line between this point and that point, it looks like this. Okay, different slope. So I don't have an actual tangent line here at this red point, right? That's kind of what I'm trying to get at. Because from the left-hand side, the tangent line looks like this. From the right-hand side, the tangent line looks like that. And some, you know, a quote-unquote line that looks like this is not a line. So long story short, if you see a kink on the graph, the derivative does not exist at that point. So we're going to go over here and scan this graph. Do we spot any kinks? I'm scanning left to right. There's one of them, right? So the derivative does not exist at 1. So where is it not differentiable? X equals 1, and then we're going to look at other places. Okay, what is another situation in which the derivative might not exist if you're looking at the graph? Well, so the second one is, what if the graph has some sort of jump discontinuity? All right, so here is an example of a jump discontinuity. So what if this is my a value? That would be up here since that's included. Let's play the same game. If I pick a point to the left of a and I draw the secant line, and then I make that point closer to a and redraw the secant line, you can kind of see what's happening, right? This secant line slope is approaching an infinite slope. So I can already stop there. If the limit is infinite, the limit does not exist. But just for completeness, what if I had, not noticed that and picked a point to the right of A and drawn my secant line? Okay, and then I make it closer, and then I make it closer. You can see I'm approaching the same problem. Well, actually, for this particular graph that I've drawn, there isn't too much of a problem. If I approach from the right, I would have maybe something like that, the way I've curved the graph. So this slope would be fine, but this slope over here that we just talked about goes to infinity. So again, we don't have a tangent line, and 1/2, if you will, of the tangent line has an infinite slope. So again, the takeaway from this is that if you have a graph segment portion that looks like this, it has a jump discontinuity, then the function is not differentiable there. Let me just point out that this also generalizes to a gap discontinuity. So what if the graph looks like this? Okay, and this is your A. Same thing, right? Because if this is the point, and I pick a point over here, make it closer, you can see I'm approaching an infinite slope. So same problem. So any sort of jump or gap discontinuity, function is not differentiable there. Going back to the example, scanning from left to right for those instances, here is one. This is a jump discontinuity, so we're going to add x equals -1 here, not differentiable. And then continuing to scan this way, over here we see another gap discontinuity, so x equals 3, we will add that there. All right, last way that a function may fail to be differentiable that I will discuss, right? There are lots and lots and lots of ways, but 3 is always a good number, so let's talk about a graph that looks like this. Try to draw it as best I can. So what am I trying to draw here? I'm trying to draw at x equals a vertical tangent line. So unlike the two examples I've just shown you, if I pick points, from the left and from the right, I do get a tangent line. Here I am picking points from the right, my secant lines are converging to a tangent line. So there is a tangent line. The problem is that it has an infinite slope. And again, the derivative is a limit. If the limit is infinite, it does not exist. Therefore, derivative does not exist at places on the graph where we have a vertical tangent. So looking at this graph, I don't see any place where we have a vertical tangent. So there is nothing to add. And what else might go wrong? So the last thing that might go wrong that I'll point out over here, kind of buried in the definition of the derivative, is this. In order for you to calculate f prime of a, you have to know what f of a is. In other words, it has to exist, it has to be a number. So if there are any places where the function is undefined, the derivative is not going to exist there. And that's our last place here where the function is not differentiable at 2. We have a vertical asymptote there. That means the function is not defined there. So we will add this to our list. Great. And then if we just order it here, the points are x equals -1, also 1, 2, and 3. Okay, so those are the places where the function is not differential. Great. So now let's talk about continuity. This one will go a little faster. We've talked about continuity quite a bit in the previous videos. I will just remind you about continuity at a point. This may be in video 7.2 maybe, or in the 7s. So I would check back to those videos if you want to review this concept. But remember, long story short, for continuity, we have a 3-pronged criteria for the continuity of a function at a point. The function's value has to exist there. F of c has to be a number. The limit has to exist as x approaches c, and those two numbers have to be equal. Okay? And remember, the limit existing here, this is a 2-sided limit, so that itself has a 3-pronged criteria for existing. Okay, but long story short, when you're looking at a graph, remember the takeaway is a function is continuous if you can draw its graph without lifting your pencil, right? So this comes out of the intermediate value theorem. This is a continuous curve that I've drawn. It's not a function because it fails a vertical line test at a bunch of places, right? But if I draw a function that looks like this, and then oops, oh, that's nice. Apple filled it in for me. And then I have to hop over here and continue drawing. Well, I've lifted my pen, so that's a discontinuity. Vertical asymptotes work the same way. If I draw, I go up, and then there is a vertical asymptote here, and I have to go down this way. I've lifted my pen. Okay, so in terms of the math of this definition, right? If the function value does not exist, discontinuous. So already we know here at x equals 2, we have a discontinuity because the function is not defined there. So we'll add that up here. Also, if the left and right limits are different, then the two-sided limit doesn't exist. Function is not continuous. All right, that happens over here. As I approach 1 from the left, I approach 2. As I approach, -1 from the left, I approach 2. As I approach -1 from the right, I approach -1. Limit, two-sided limit does not exist because 2 and -1 are not the same number. So at x equals -1, I have another discontinuity. And then continuing to scan the graph, look at what happens at 3. If I approach from the left, my y values tend to 1. If I approach from the right, my y values also tend to 1. So the two-sided limit exists, great. And the function is defined at 3. It's equal to 2. So f of c exists, great. However, these y values are not the same. So discontinuity there, right? So this is the gap discontinuity we talked about. So x equals 3 is another point of discontinuity. Great, so those are all the ones that I could find. So I'm going to order them, -1, 2, and 3. All right, now what I wanted to do, I'm going to move this around a little bit, is to just at the end of the video here, compare these for you. Notice that everywhere the function is discontinuous, it is also not differentiable. Okay? So there is a theorem that tells us how continuity and differentiability relate. And this is theorem 3.1 in the Calculus Simplified, in the textbook we're using, which says that f differentiable at x equals a implies f continuous at x equals a. Right? So if you are differentiable at a, you are continuous at a. Right? There's something called the contrapositive, which is a fancy term for taking this if then statement and swapping the hypothesis and conclusion and negating them. So here is the contrapositive of this statement, which says, if f is discontinuous at x equals a, then if f is discontinuous at x equals a, then f is not differentiable at x equals a. Okay, right? So I took f continuous at x equals a, conclusion of this theorem. I put its negation, its opposite, as the hypothesis. I took f differentiable at x equals a, hypothesis of this theorem, and I put its negation as the conclusion of this statement. So it turns out, and this is an exercise in truth tables, which is part of what you would do in a course in logic, or just later on in the curriculum, a real analysis course, or any sort of introduction to proofs course in a math curriculum. You show that the statement of a theorem and its contrapositive have the same truth value. So we know that this theorem is true. We can prove this, and therefore we know this contrapositive, the statement, is true. Which tells us, therefore, that if a function is discontinuous, then it's not differentiable there. So what we're seeing up here is a reflection of that fact. The function is not continuous at these 3 x values, therefore it is not differentiable at those 3 x values. There is another value, though, at 1, right? X equals 1. So let's go back to 1, see what was special about 1, right? And this is where it pays to think more critically about the logic. At x equals 1, the function is continuous, right? I can still draw my graph without lifting my pencil, but it's not differentiable. So the thing to keep in mind is that differentiability implies continuity. Not continuous implies not differentiable. That's what we just talked about. And that is what is true. However, what is not true is that continuous implies differentiable, right? The first two are true. They are theorems. This one is very often confused with these two results, right? This one is not true. It's true sometimes that continuous functions are differentiable there. Take this piece here, nice and continuous, and I can draw all the tangent lines I want. So continuous and differentiable, check. However, take this piece here, continuous, but not differentiable at that point. Okay. So again, the quick recap is that differentiability and continuity are intimately related by this theorem and its contrapositive, but be careful, right? Those two statements are true if you use them the right way. If you're differentiable, you're continuous. If you're not continuous, you're not differentiable. However, what is not true in general is that if you're continuous, you're differentiable. Okay, so hopefully these two segments of the graph illustrated where that may be true, that may not be true. Great, thanks for watching.